All right, so picking up where we left off with the cerebrum, this is a reminder that, like we will see in the spinal cord coming up, anterior part of the central nervous system deals with motor, right there, and it will send its messages from the beginning, front part of the brain where we're thinking of ideas, to where we have them pre-planned and all the motor tracks are already programmed for us, and we'll go down this primary motor area straight to the spinal cord to the corresponding muscle groups, whereas the posterior part is receiving information coming up from the senses. And you see the same in the spinal cord. We use the dorsal tracts to send information up. We receive it here on our primary somatosensory cortex, and then it'll move back into the association area. And we also receive visual here and the other senses in the temporal. So when we say we have a motor area versus a sensory area, those are really just those minor two strips with association areas beyond, and they're either coming toward the center or from the center back, depending on where we are in relation to that central sulcus. So if we start in the frontal lobe, we'll see the three main areas I talked about here, where we have our initial ideas of how we want to move, and these are considered also our higher function areas in the prefrontal cortex. But here we're just primarily looking at what happens when we have a motor plan, which is what we built together over years of practice by specific motor commands, remembering that right hemisphere talks to the left and left to the right, that we've laid out all the muscle interactions that we would need to make the coordinated motions that we've practiced over and over. And a reminder that in the business of therapy, we call this praxis, which requires practice. Nice rhyme there for us. But praxis is our ability to take a pre-programmed motor pattern and just play it. And that's why we can get through most of our day without having to think much about what our body is doing. So it shows us here doing a complicated thing like playing a guitar. It's all set because of the time and waiting to spend on practicing. A specific area for speech is found in the left hemisphere in that same strip. We call it the motor speech area, also known as Broca's area, and that regulates the motion specifically of the mouth, tongue, throat to allow us to make sounds that make sense to ourselves and others. The primary motor cortex, or the actual lineup to the spinal cords talking directly to muscles. So here we'll see a two-step process from brain, which we call upper motor neuron, to spinal cord, which we call lower motor neuron, to the actual muscle, and that's the primary motor. And then the frontal eye fields also fit in here, same as the motor speech. We need specific coordinated activity to make our eyes work, and that's where we have binocular vision by combining what's coming out of both hemispheres. So that's a good summary of our frontal lobe. The sensory part is spread across multiple lobes, but not the frontal. Remember, the frontal is primarily for thinking about and then doing, where everything else is processing what comes in and then taking the weight of it and saying, all right, this is a good sensation or an upsetting memory, and all that is our subjective weighing out of what we receive. Everything that comes in through sensory, except for the sense of smell, there's always one exception, is first going to arrive in the thalamus, which sits deep inside under the insula. And then the thalamus will filter, give us a chance to decide how important that is, and then put it in the appropriate part of the remaining brain. So when we look at all these different areas, we'll just name which lobe handles which sense, and knowing that all except olfaction or smell come through the thalamus, that gives you a sense of their pathways. Parietal deals with touch. Begins on that first strip that we said was the post-central gyrus, which we call the primary somatosensory cortex. It's a lot of letters. And that's where we receive the information and process it. Similarly, through all of these senses, we're going to next send it to an association area where we're going to make sense of it and line it up with things that we already understand. So anything that we've touched, we'll have a memory of that, and then we'll expect a certain texture or weight to something when we go to pick it up. That's parietal. Occipital takes vision from the eyes through cranial nerve 2 into the thalamus through some pathways back to the occipital lobe, and then again we're going to arrive in a primary sensory area and then move to association areas. In this case, it goes like a bullseye, starts in the back and spreads out radiation to give us that sense of, I recognize this, have I seen this before? Auditory works with both temporal and the olfactory, so they both come in through here. So in the case of auditory, we're going to go through one ear, actually through the entire brain, and come out the other side to the opposite temporal, and vice versa. Once again through the thalamus. Olfactory, and once again, like we said about the motor area and the association area, we have a very specific region here called Wernicke's area, which is our ability to recognize sounds that will help us with language. And in most humans, these are located in the left hemisphere, so we'll see both the sensory and motor components of speech hidden over here, and they talk to each other, and loss in either of those areas we call an aphasia. So Wernicke's aphasia is an receptive aphasia. We don't understand what is being said to us, so much as if everyone's speaking foreign language. But the Brokaw's aphasia in the frontal lobe is going to be an expressive aphasia where sounds that we try to make don't make sense to the listener. It could be the wrong message. I often see clients who will try to say simple answers like yes or no, but their mouth isn't saying what their brain wants them to. So if they're doing something like no, no, or yes, trust the head movement more than the sound that comes out, because the sound, if they're dealing with left frontal lobe brain damage, the sound that comes out is often not what's intended. You'll see the frustration on their face, or they'll come out with curse words if they're not used to saying that, or revert to an older language that they learned as a child, primary tongue that they've learned English since, that may be lost in the damage. Olfactory mention goes directly in to deal with the sense of smell, and that is really close to what we call gustatory. Most of what we taste is derived by smell. So that area is in the insula or beneath. As you see a little probe there pulling back our temporal lobe to see the insula, which the insula wraps around the thalamus itself. So again, giving functions to specific regions. Here's the prefrontal, which is going to give us our idea of, I have an idea that I want to execute. This is what we call the higher order thinking that we reserve for humans, and it gives us the ability to hold our concentration, make a decision, make appropriate choices, plan for the future, and is part of what we consider our personality. The famous case of Phineas Gage, who had the railroad tie go up through his face. You remember him from Abnormal Psychology? He had no physical damage from it, but he changed his personality, and that was a very early case study where they said, must be something up there that made Phineas Phineas, and now he was no longer Phineas. Then the Wernicke area, as I mentioned, that is kind of wrapping between three different hemispheres. That is also playing with the idea of how our senses can be confused, I guess. Sometimes you'll hear people who detect sight and sound and hearing overlapping, and taste particularly. They'll say the letter 7 or the number 7 is always blue, or they'll have a taste association with visual. So these are when the lobes share information and we just process it differently. And that's synesthesia. This, I think, is a pretty awesome picture, but it's a little weird to look at the first time we see him. The homunculus means little man. So the little man in our brain is going to take, so if we go back to how we split down the center, we're going to have one hemisphere over here and another here with a pretty good cut through. Did you guys, you didn't do the brain yet, right? Is that this week in lab?
I did that section.
Yeah.
No.
Okay, so if you did it in human bio with me, you'll remember, and you'll do it in lab this week, that there's a sliver of our dura going right down through the center, and you'll have to peel that off and cut it out. And then you'll notice that the only connecting part between the two hemispheres is this area called the corpus callosum. It's a white matter, and you'll be able to open your brain and just peer down and see it. When that's removed, we see that we actually have gray matter throughout, which means the outer portion. So if I did the gray matter in this darker color, it'll be all of here. And then the white fills up the inside. Of course, there's some gray islands in here of our basal nuclei, our thalamus, and we're going to have the big gap where our ventricles run through. But the majority of this is white matter tracks going around and around, front, back, up and down. I think we did those before where we named the different directions. But anyway, this region here, the gray matter on the outside, we've actually mapped it out, and that's what we're representing here. You sense your toes down in here, up to your ankles, and your knee, your leg, and then we bend, and we come around the trunk, and then all the rest of it, hand, face. So the majority of our brain tissue is trying to figure out what we're detecting here, and in the mouth. And that's when we say the map, the motor map. We're doing motor now. This is the movement, but it's identical with a few exceptions on the sensory side, meaning what we do with our hands and face and how we feel our hands and face is the majority of what the brain is concerned with. So unfortunately, this is also the area where we're more likely to have damage with stroke. This little protected area inside is usually preserved. So when you pull out a specific spot, say, okay, here's my middle finger right here, meaning, oh, hello, middle finger, you jumped in on me. If I use the part of my brain that says I want to do an action, I'm going to send a signal there. That will send a signal down my spinal cord by crossing, coming out on the opposite side. This would be my left side case. I'm not going to raise my left little finger, but if I were to, the message would go to my spinal cord and it's come out here and say, let's do flexion. And I did flexion with my left middle finger. So that's the specific area. If we were to excise that part of the brain, I wouldn't have any control over that. Neuroplasticity gives us the hope that with damage to this area, so if you have a stroke, a brain injury that causes bleed in the area or any other kind of infarct, we can use the surrounding tissue to pick up the slack and help us out. And sometimes we can cross from the other hemisphere to help. But we do see return, it's just a longer road back. We also know that if someone loses a hand, for example, they may have all this region of the brain that's going unused, and it gets a little antsy, and sometimes we have what we call phantom pain. So let's flip to this side, which is the same picture, just we're just showing right, left to make it a nicer visual for you, but it's just that strip behind it. So if we jump back, you'll see red strip here, your pre-motor, or your motor region is your pre-central gyrus, and then we jump over here, and we just see the strip behind. Post-central gyrus, that's your sensory region. Very similar lineup. We just have a couple extra guys down here that we didn't have before. And then we're going to add face, tongue, throat, and hand as the majority of what we're feeling. So sensation will travel up from the spinal cord through the dendrites, arrive on the opposite side of the spinal cord, climb up to the brain, pass through the thalamus, and show up somewhere up here. So in the case of the person with an amputation, this part of the brain has nothing to do. Nobody's sending him signals anymore. So in some cases, it gets a little antsy and we feel things that aren't there anymore. We feel our hand, we can feel it opening and closing. The worst scenario is when we have pain in that area, and it feels like a constant pain. And there's certain therapies that we've found can be quite effective in helping untrick the brain, because the brain doesn't know what's going on out there, and we try to teach it otherwise. And if you ever heard of mirror therapy, we will sometimes take, I've seen it less effective with stroke, but fairly effective with amputation. So let's say I have a feeling that my hand is pinching all the time. My nails are in my palm and it hurts, and my hand is just cramping, but there is no hand. So if we put that residual in behind a mirror, and usually we make a little box out of it, and then I put my other hand in front of it, and then I look in the mirror and I see two hands. I open this hand, I see two hands open. Sometimes that's enough to tell the brain it's okay. And it's pretty amazing when those work. One of the craziest scenarios of a mirror in my practice was when we lose the left side of our body through a stroke. And I might have mentioned this with vision, but I'll add more. But we tend to have the left side of our brain that takes over. Remember, it's opposite, so it's a right-sided infarct. I've lost sensation or motion over here. I usually lose the visual field, but the personality change that often comes with that is a denial, a feeling that, well, this isn't part of my body. My brain just accepts it and moves on. And you'll see people struggle to recognize their body parts. They'll run into things. They'll have trouble with that. So one of my early exposures to this, and just kind of put me on the path to want to study the brain more. I had an older woman who had paralysis, and she had her hand, and I would always put it in her lap to, we could work on therapy with it. But she had no idea that it was her own. She'd refer to it as her dead mom's. It is a, she didn't know what it was. Or I'd have my hand nearby, and she'd grab my arm and try to move it. I said, "No, that's your hand."
Dementia?
No, it's a feeling of, and it's hard to describe this personality change that happens, but I look at it this way: the right hemisphere has a better view of the big picture. It understands the entire world and sees us as part of the universe and all that, if we go that deep. The left hemisphere is very logical. So in the brain's logic, it's like, well, if I can't feel it, it's not there. If I can't see it, it doesn't exist. And it's really black and white that way. So when the visual field cut happens, nothing to the left of me exists anymore. If you couple that with, I can't feel this arm, you get this really, I would call it creepy, event that we call hemi-neglect, where we just neglect this side, it doesn't exist. So those scenarios were definite sign of that. So I thought and sometimes this works, but I thought, what if I put her in front of a mirror and have her find herself in the mirror, and there she was, combing her hair, just half of it. We see people just shave half the face. It's just fascinating. And I said, it's like, the hole right down the middle. The whole thing doesn't exist. Wow. So I said to her, "Do you see your arm?" "Yes, I do." "Can you pick it up?" And I watched her touch the mirror, trying to get her hand out of the mirror. And I'm like, that's perception. There's something in there that has disconnected her from reality. Sometimes those recover, but in the early stage post-stroke, you'll see some really, really bizarre things and it really tells us that our two hemispheres, without this, are operating, seeing two different things. And we combine them and make sense of our reality. But if you take one offline, you get a really interesting mix of symptoms, personality changes, and paralysis and weakness. As you can imagine, if we go back facing you, if we put the left side in jeopardy, and over here is my Broca's motor area, if I have a stroke on this side, now my right side's paralyzed, I probably lost the use of my dominant hand, because 70% of us are right-handed, but now I can't speak, and I can't understand when you speak to me. So those, they know it's their arm, but they're weepy because they're like, I can't talk, I can't use my main arm, I'm really upset and depressed. Where my left guys who get damaged on the opposite side, they tend to be pretty stubborn, and to use a word, and in denial, and dangerous for that reason, because they'll get up. They'll be the ones who get out of their chair and just kind of fall because they don't understand, they want to get in the car. Well, why can't I drive? Well, you can't use your left side. Well, just get me in my car, I'll be fine. So we'll wheel them out to the car. We have to go through this sometimes to get to that stage. Wheel them out to the car and say, okay, here's your keys. And they can't get out of the chair. And then if there's some point where we have to say, let's go back to the therapy room and process this. But it's really difficult. If you've had that happen to a family member, a loved one, or it will in your career someday, if you run into stroke care, you might remember these scenarios and help the family understand mom or dad or whoever your loved one is just going through some stuff. Their brain is kind of resettling and figuring out where. But if if this is your reality, if you know that this is where you are, and I take this away through damage, you don't have any part anymore. You don't have any awareness of it. So that's where we run into trouble. You'll see people, curl their arm up into neglect and lose function because there's no communication anymore. So that's a deeper topic, another years of study, but it's just fascinating. I wanted to throw those scenarios out there to give you a sense of how this all relates to what you'll see in your future practice. This is actually, I thought I said this already, but I did not. So let's look at what we mean by how the white matter talks. So if we go back to the idea that the gray is on the outside, which are cell bodies and little short axons we call interneurons of the little short interneurons that talk to each other. But the majority of the brain space and the outer columns of what we call the spinal cord, or tracts, are all white matter that are sending signals from here to wherever it has to go. Those major types are called association. We're going to be talking within a single goal. So I'm going to get the information. We already talked about this actually when we said I'm going to take a sensation and associate it with something I've already detected. So I saw something, I associate it, I recognize that. And that's when we learn language. I recognize these letters. And over practice, I can make the sounds that go with it by using my posture here. I think I told you this last time, but the myth of the 10% brain, we only use 10% of our brain, based on these two strips. They're the only ones that will react directly to stimuli, where the rest of it, if you were to poke at it or prod it, the person wouldn't detect anything. So the reality is we use all of it all the time, but these are the two direct areas. Unfortunately, these are also quite common in stroke because of where the middle cerebral artery feeds, which is one of the big ones that goes. But make no mistake that we're using our brain to its fullest as often as we can. And this chatter is going on constantly. We're always reassessing and setting up. And what's not in this picture is the cerebellum down here. Every time you think about moving, he's going to go and critique you. Nope, that wasn't good enough. Let's try again. This is the plan you had. You screwed up. Let's do it again. You build your motor skills that way. So association tracks work within the same hemisphere to let sensory know what motor's about to do and vice versa, and then associate all the sensations that do come in with things that we recognize. The commissural tracks are going toward you guys. This is the corpus callosum. So if I turn this whole picture that way, I happen to have blue, which was convenient. These blue dots would represent axon back and forth. And you'll actually feel that if you get a chance to crack the brain open or just watch as it's being done. And you can cut through it with you can actually just peel it apart like an orange, just two little fibers rip. They're just tiny, tiny strings covered in a fatty material that we call myelin. Remember, for the role of the microglia, the oligodendrocytes wrap it here. If we go out in the body, that's the neurolemma Schwann cells. So it's the same coding, it's just how we name them and what they're doing differently. So the majority of our left to right talk is called the corpus callosum, and then we have a little anterior commissure way down here that gives us one more chance to chat. But otherwise, these hemispheres are separated from one another. So there they are, going green. No, that's blue. Blue left to right. And then the greens are projection tracks that either start in the brain and go down or arise up from the spinal cord to the brain. And everything's going fine until we get just below the pons and we hit the medulla and we're like, you know what, we decided we're going to change lanes. And we don't know why they do this. We assume it's some form of protection, but all creatures of the brain do this. So the right side comes up and right about here says, I'm going over here now. Flips, and we arrive on this hemisphere. Our thalamus will process sensory and put it where it belongs, and then the motor will send it directly. Just remember when we get to the spinal cord, if it's coming out as motor, it's going to go down that anterior part of our spinal cord, which is called the ventral. And then if it's going to be sensory, it's coming up the back side, which is dorsal, and will end up in the back part of the brain. So again, you see here, this is the gray matter. So we could actually remap the whole thing: toes, knees, hips, trunk, head, all the hand, all the face. And same whether it's motor or sensory, very similar. So projection tracks go up or down, and I think I wrote this down for you, but anything going up has to be sensory, anything going down has to be motor. So ascending, any of those words that mean up or incoming, are all sensory backside. Anything coming down, which is descending, is motor. Did I say motor? I think I meant to say sensory. I hope I didn't say motor. We rephrase that just in case I said it wrong. Coming up the back is all sensory. So it's ascending, it is ventral, or I'm sorry, dorsal or posterior. Where the anterior coming down is always motor, which would be ventral and anterior. Those are the projections. Commissural are just left to right. Make sure the two hemispheres talk to each other. And this is what they would cut in the split brain experiments, and there's some interesting YouTube videos, maybe you've seen them at Normal Psych as well. You present someone with something that only one eye can see, they may say something that they saw with the one eye and then draw something with the opposite hand, because that side doesn't speak, but it will draw. It's just fascinating stuff. And then here I hinted at these guys. These are our little cerebral nuclei, also called basal nuclei, but you may have heard of them in their older name, basal ganglia. So a ganglia, which we'll see very soon, is a cell body cluster out in the peripheral nervous system. Cell body clusters in the central nervous system are the same idea, but technically we call them nuclei instead. I find that confusing because we have a nucleus in a cell and we have a nucleus in an atom, but it's the way it is. So these are the nuclei in our basal part of our brain, or the base of our brain. But if you heard the word basal ganglia, it's the same thing, we're just using the older language. So these are your two lateral ventricles, your third going down to your fourth ventricle, and then over here, you'll see some interesting little clusters inside. You can see with the fibers here, how fibrous this is. Corpus callosum, ascending and descending tracts. So these masses of gray matter will provide a calming effect to the chatter of the brain and give the motor movements that come out a smooth quality. When they're impaired, you get jerky, involuntary motions, which are associated with Parkinson's and other things. You'll see Parkinsonian-like effects in dementia when the brain becomes damaged through plaquing and so on. So you don't have to know these specifically, but these are the thalami. And then these little guys over here on their sides each have their own name, but they are just involved with protecting our motor plan to be smooth. So then we've peeled away the cerebrum. The diencephalon is probably the hardest part to see on a dissection, also because your brain's going to be super tiny. The brain can dissect only about that big. But this, because there's so many fibers going, to peel it out and see a thalamus intact is pretty tricky. The models show a real nice job. If you pop the temporal lobe off, you'll see a little ball in there, usually with some insula on the outside, but if you turn it around, it's an egg shape. So our thalami are egg shaped and they come up like that. So there's one of them, you see this little stalk going between them, a little stalk, and that just holds them together. So above it is the corpus callosum we've mentioned a few times. The fluid of our chambers is going to circulate through here, so our cerebrospinal fluid will run through here, and the third down to the fourth ventricle, and the laterals on the side. The three portions of what we call the diencephalon, or center of the brain, the top of the brain stem, are the thalamus, which is two of them. Thalami are the two egg-shaped clusters that process all incoming sensory information, except smell. And it says nearly all. Olfaction is the exception. Then it has an emotional component to it that bypasses that and will hit our emotional centers that we'll name in a little bit, the limbic system. And then it will trigger scent memories that will be stronger than many other memories. Hypothalamus is the mass of tissue below. The hypothalamus is responsible for bridging our nervous system, our endocrine system. The pituitary gland is its product, as it sends its little stalk is called an infundibulum, and it drops down here into the sella turcica of the sphenoid bone. If you remember that as a little Turkish saddle, you sit it in there, and that will never be preserved on a dissection because when we pull it out of the brain, that little stalk falls off and it's gone. But you will see this optic chiasm. There's a cross that goes from eyeball to eyeball, and then the pituitary sits right behind it, so that's a good landmark. On the human, it's like this, but on your sheep, it'll be more like that, because his eyes are over here, or hers. Because they are prey, so they're always looking where we are predators, so we're focusing forward. So we have binocular vision, they do not. They're seeing all of this in the periphery to watch, and their nose is dealing with what's in front of them, which is usually grass, whatever they're up to that day. And you'll also notice that their olfactory bulbs, which for us are think about the size of my thumbs in here, theirs are like the size of a whole fist, way out here. Because they are huge, they're going to be drawing in scent information, and for them is it safe to eat or not, really, is their main, and is it time to mate or not? Who's mom? And that's their main role in life, where we have diminished sensory organs because we've traded it for other things. But you see the same thing in a cat, dog, or anybody that uses smell to work their major impression of the world. Gigantic bulbs coming out, which we call olfactory bulbs. So looking ahead, that's cranial nerve 1, is cranial nerve 2, the optic is coming back. Then we just work our way down, 3 through 12, work back and down the spinal cord. Just, I shouldn't say spinal cord, they end up at the base of the brainstem, where some of them do enter the spinal region, but 1 through 12 are all in that little region there. So hypothalamus is in charge of all of the regulatory functions of the body, and it uses the pituitary to do it. The pituitary is also called the hypophysis. You'll get to him in AP2 sometime, but you'll learn there that the back part of them is called the neurohypophysis, which is a direct extension of our hypothalamus into the posterior portion, which we call the posterior or neurohypophysis. And then the anterior part there is called the adeno or anterior hypophysis or anterior pituitary. There's a ton of hormones come out of here, and just two that come out of the back. And that's that. And then finally we have the pineal gland. You'll see that pretty large on the sheep. So when the head comes forward, if you get that view, when you lean, and another thing you remember, our spinal cord goes like this out of our brain, there's gonna go like that, because they're forward. So if you lean the spinal cord down and pull the cerebellum up, you'll see these lumps. You have to pull the Mr. Cerebellum out of the way, and you'll see a big little guy sticking out in the middle. Pine cone, which is where his name came from. These little guys here on the back of the midbrain, they're going to have a gigantic superior one, where ours are equal size. But these are called the corpora quadrigemina, and the upper ones are called superior collicula. So their superior collicula is super superior compared to their inferior, where ours are equal in size, which we call them quadrigemina, which means basically quadruplets, but 4 twins. So you'll see those clearly on the back of the sheep. And there's a nice shot of it in the should be in your lab materials, in case you don't get in up close on it. Oh, and since I talked about it and say what it does, we call that our internal clock, our biological clock. It keeps track of our cycles and it secretes melatonin to help us relax at night. And that is, while not tied into the eyes at all, it receives the same stimuli from sunlight that will tell us what's going on. If you work a night shift, for a while, it's pretty difficult to switch your sleeping patterns because we're programmed to go down when it's dark and wake up when it's light. Now we're into the brainstem. So you'll see the same parts here: thalamus, hypothalamus, the pituitary gland, pineal gland, corpora quadrigemina. We're going to save this for later. And remember, this is a great cut when you also do the brain. You'll see this arbor vitae of the beautiful white matter of the cerebellum. That's something I always look forward to, seeing that, how it looks. Anyway, we're down here. The midbrain, pons, and medulla are the three components of what we call the brain stem. And we just go from descending order. So the midbrain's up top. The pons is a grape-shaped lump that comes anterior, and it is a bridge between the cerebellum and cerebrum. It's this huge network that goes back and forth. Pons means bridge. And medulla oblongata is the top of the spinal cord, a swollen area just as we're about to enter that spinal cord area by going through the foramen magnum and the occipital bone. So all of our rest of our cranial nerves come out through here, and it's a pathway of fibers running to and from the rest of the brain. Anybody that's going up has to go through that first. So you'll see this little line here going down represents our central canal in the spinal cord. So all these posterior fibers are rising. They're going to jump in and up, and all the anterior fibers are coming down. And they're going to cause some motion out there in the bottom. So in the midbrain, we're pulling out, we already did cranial nerves 1 and 2. So 1, which is olfactory, you would be sitting over here. In our case, right about there. In the sheep's case, way up here. And number 2 is this piece right here, that little ball represents where we cross, which is called chiasma of the optic nerve. 3 and 4 show up in the brainstem. We'll name all of them later, but just let you know where they are so when you see it, and you rarely will see more than 1 and 2 on a dissection. They get pretty shredded, but if you make out any, just know 3 and 4, and then we work our way down. So our connection in the midbrain, again, is working with our cerebellum, the corpora quadrigemina we mentioned, the visual on the top 2, and auditory in the lower 2. So the reflexes that the sheep needs are for survival. The sheep, and really any, I think of a horse when I look at how they're designed, because horses are beautiful, noble creatures, but they startle easily and they are prey. Even though we don't have natural predators for them around here, they are nervous, like, who's gonna get me? So if you sneak up on a horse, if you've ever been around a horse, you know you don't come up from the horse without letting them know you're there, because you will get boom. But they are skittish that way, and their eyes are looking all the time. And the same idea with any prey animal, that we have to have highly developed reflexes so that any sound or any motion out of the periphery, I'm ready to fight or flight. And they're running at a low level of tension all the time. So working with those large animals, we do that with therapy a lot for kids with tone issues or adults with sensory processing, you name it. Horses are a great therapeutic partner, but we have to be really gentle with them because they are also very sensitive. And that helps actually with the therapeutic aspect. We work with our folks with trauma and other issues, and you can say, when you're calm, the horse will be calm. If you're stressed, the horse isn't going to let you near them, and that helps them learn how to calm their own body. So that's your corporal quadriceps. Anyway, visual top and auditory the bottom. And it just means body of 4 twins or quadruplets. The colliculi are their fancy names. So you have the superior and inferior colliculi and even little hills. So when you see them from the back, they've got 4 little hills. And again, you'll see 2 giant hills and 2 tiny hills with a pineal gland poking through. The next group of cranial nerves, 5 through 8, show up down here in the region we call the brain stem pons. The pons is the grape-shaped ball. That word literally means bridge, and it is what we use when we describe the Pope's role as a pontiff, is a bridge between heaven and earth. So this is our bridge between, we can go with heaven here, the big brain, cloud, and then the rest of the body. But specifically talking to the little brain, or little cerebrum, the cerebellum. So you see a ton of functions here. They're all based on reflex and things that we are not directly in control of. So brainstem damage will cause issues in our survivability and our ability to be alert. We'll see in a moment that there's a reticular activating system that runs through here that turns the brain on, the upper part of the brain. The cerebrum makes you alert. So if there's damage in here, we often end up in a coma state, which is Greek for sleep. And we are running the brain, but we're offline. We are not there to interpret or tell the outside world what's happening to us. A laundry list of things that we take care of here. We're going on to medulla, which is the last piece. Again, right about here we have the hole, which we call foramen magnum, where now we're calling this spinal cord. Here we call it medulla. When we call it spinal cord, we're going to start saying this is the region of C1, and that's where our first cranial nerve cervical nerve comes out. When you get to those, I don't think that's IAP2. Just remember that the very first nerve that comes out is not C1 like the vertebrae, it's called C0. Sorry about that. I would have named it C1 and gone down, but that's okay. So C0 comes out, and then we work our way down. You can go back. So, well, let me rephrase that actually. That's not, that's what, I just told it totally backwards. That's what I would have called it had I done it. They call him C1. As he comes out here, C1, 2, 3, 4, 5, 6, 7. And then each of those associates with a vertebra. So this is where I've been positioning silently in my own head to get that called C0. And we're done with that. These are our 7 cervical vertebrae, 3, 4, 5, 6, 7. And then we start with T1. When you're naming the nerves, you go C1, C2, C3, C4, C5, C6, C7. Beautiful. You would probably call that T1, right? No, they call it C8. And then it goes T1, T2, T3. That was my issue. So, sorry I misspoke. So C1 through C8 are the cranial nerves, even though there's only 7 cervical vertebrae. And then we go T1, T2 down. What do you do? No one's going to change it. It's like you're trying to get something through Congress. That's the way it is. Cranial nerves, I've never actually petitioned anybody to change that. When I teach it, I try to remind you that there's a bonus cervical nerve in there because who would think? So when we get down to the medulla, which is the last of the cranial nerves, and I think I also just stumbled my words and said cranial instead of cervical. Just be careful on that. Cranials are Roman numerals 1 through 12, come out of the brain, where cervicals are the first 8 nerves that come out of your spinal cord, and then they continue down. The rest of them make sense. T 1 through 12, L 1 through 5, and then some sacral and coccygeal, for a total of 31. Here we have 12. So it seems there's an infinite number of things to learn, but you only have 12 Roman numeral cranials, and then 31 just know by number. The only trick is that there's a C8 in there. Okay, no C0. Nobody listens to me. So the cardiac center and the respiratory center and the basal motor center are all in here. And there's a redundancy built in so that we're working between medulla and pons to make sure that we breathe. So by redundancy, I mean, and we'll do this in the respiratory center way at the end of next semester, maybe in the middle, I guess. You're going to say, I'm going to send a signal down to the diaphragm to make sure that it goes to breathe. but I'm gonna have the pons nagging me to do it again. Don't forget to breathe, don't forget to breathe, and it's just make sure that we continue to breathe. And that controls our rate enough for breathing. We also have reflex centers, and we have some coughing sound effects just to underline that it's happening here. It's perfect. Please don't do the other sounds. You can help it, sneezing, gagging, vomiting, we don't need all that. But all the facial nerve, cranial nerves that come out are involved with reflex that will allow us to do these things. So there's our cerebellum. And there's, again, that beautiful shot of it sliced here. When you look at it from behind, you'll see it's two large hemispheres that kind of look like a hairstyle to me, like an old crazy hairdo. And then down the middle, what would be the corpus callosum in the brain, or cerebrum, here is called a vermis. And the vermis means worm shaped. You'll see it again in the vermiform or worm shaped appendix, or vermin in other words. So it's a little worm line and then a big hemisphere, and then we have two lobes compared to the file up there, anterior and posterior. So when you slice it, you'll see the fourth ventricle here, the third was up there, and then we directly send the fluid down into the central canal. The arbor vitae is the white matter that connects to gray, and here when we call them sulci and gyri up there, the word for the folds here is folia. So once you have the brain in front of you, you can almost flip through the pages of this cerebellum by going along there, and you'll see how tiny, tiny little ridges they are. Anytime we do this in the body, cerebrum, cerebellum, we'll see it in all of our organs inside. We are trying to increase surface area. So the multiple foldings, if we had it laid out, would be like that big, and we crunch it up into this little folded ball. It's our fine tune. Make sure that our muscle activity does what we ask it to do. So our motor plan is way up here in the frontal area and says, boy, I'm gonna do something awesome. I'm gonna jump up on this desk. You walked into this, I was gonna say, jump on the desk. No, I can't do it. So too bad. I was gonna do it too. But if I did the epic fail that I expect I would do if I tried, I would then have my after I get through all the ouching, the cerebellum would say, let's not do that again. And if you do, make sure that you have these conditions. And that's how we practice. So when you're learning a new skill, your cerebellum is highly involved. When your cerebellum is offline, not working correctly, say alcohol is involved, and your frontal lobes affected by the alcohol, we think we can do all kinds of things we can't do. And a field sobriety test is testing the cerebellum, the same with your eyes closed. Can you bring your hand to your nose? There's other ones, none of us would know what they are, but they ask you to do things that would ask you to test your cerebellar function. So you might find yourself doing that on a client who suspected an injury in the hospital to see if their cerebellum is affected on the way to the MRI to confirm. So it regulates movement, it stores memories, and makes sure that all of our motor paths work the way they do, and it makes sure we're moving smooth. And that equilibrium posture part is really what we're testing. That continuous feedback back and forth is through the pons. So this is our route to make sure that we're always getting information to and fro. And the other thing about it, if you're curious, is that it crosses again. So the same cross that we see here in our, we call it the decussation of the pyramids, where we take right and left tracks and switch just before the spinal cord. In the cerebellum, we do it as well. So that means that while damage to the cerebrum is contralateral. So if this was my lesion, I'm going to have weakness. Let's say that was my hand. I have weakness in the right hand down here. But if my cerebellar lesion was on the same side, which is more likely if I was, struck here, now I have coordination problems on my left side. So this person's really in trouble. So in traumatic brain injuries, strokes are easier to deal with because you can pinpoint an area and say, all right, this is what I'm expecting to have happen. When you take a full-on head injury with associated bleeding within, because we're in a closed system and we have to relieve that pressure, and until then we're killing tissue, now you have who knows what's going on. When someone comes out of a coma, any number of things can be going on, and that's the biggest message you can give to the family who are asking, when are they waking up, and if they do, what will they be like? Is you don't know. We're doing the best we can every day, but then when they do wake up, don't expect them to be the way they were. There will be something different. It may be minor, it may be, but don't pin your hopes to be the same person who went under, because whatever changes is the new person, and we have to start accepting that before we get too caught up on who they were, because it is, this is us in here somewhere. So the damage can be profound. Sometimes it's mild, but count on the not going to be the person they were. So let's look at some systems that make it all work together, because as we do in all of our studies, we break things down into parts. Say, okay, over here I'm doing this, over here I'm doing this. The brain doesn't think that way. It's all one big system running everything. So two major sets of subsystems that we can talk about that we've understood are called the limbic and the reticular. So run the limbic up here in green. He's going to kind of run in this region on both sides. And then our reticular, starting down here with like a little web of Christmas lights. That's how I see it. And they're going to send signals to the rest of the brain. We'll do the limbic first. They are wrapped around the insula, which are around the thalamus, and they're cortical structures, meaning they're inside, core. So they're in there, and they're made of the grayer matter, and they are set up as a emotional conduit. And the little dot I did here is an almond-shaped piece in the front, bottom part of what we call a hippocampus, which means seahorse. It's wrapped around. That's where we store memory. Actually, the hippocampus is the only spot we're aware of that we can make new neurons as we build memory over time. So what we call long-term memory is working through this hippocampus. The fornix and cingulate gyrus are the parts within the system. This is the one that you may know as the source of rage and really strong emotions. The amygdala, which means almond, it's a little almond-shaped thing in the front that just lets loose when you're really upset. The reticular formation are these little clusters that will send signals to the rest of the brain, the cerebrum, to bring you back online. So here's the side view of this cute little structure. We start down here with our amygdala and come up and around with the seahorse. And all these little clusters are attaching. There's our olfactory bulb. Again, you'll be surprised how much bigger the one is on the sheep. Little tract, cranial nerve 1, and then it goes. So instead of having to go to the thalamus, it runs right through this emotional center. The emotional response is how we we assign emotion to things that happen to us. And that's how we describe feeling. So I feel, not feeling sensation, but feeling, I feel bad, I feel happy, I feel sad, I feel scared. That's what we mean by that part. Fear is the big part that comes out of this limbic system, and it is designed to tie directly into the fight or flight to keep us safe and alive. So hopefully in modern society we don't need this as often as we once did when we were running around scared of saber-toothed tigers, but now we are using it for things that maybe are a little overblown sometimes. It gives us a sense of joy in life, or fear, or anything that we really feel like coming from this. It also helps us be consciously aware of life happening to us. And then odors have a direct emotional response, and that's also skunks are pretty universally thought of as, I don't like that smell. But there are things that people really get turned off by smells, and others really find them very enticing, so it's a personal response. That's an emotional response, and it's hard to override those, because there is no filter. Reticular, and we've got a little eyeball sitting there, send it in. You also see in the lab there's different animal brains in glass with some fluid that's floating around, and many of them have the eye still attached, which gives you a sense of that is part of the brain, particularly the retina in the back is brain tissue. But you'll see a little cat whose brain by a mammal looks a lot like ours, but he's got big old eyes. You'll see there's a little chicken who's got a little brain like that. And then there's who else is it? Oh, a frog, and the big frog eyes are on the side. And you ever notice that with a frog? When they pull their eyes in, they're actually like inside the skull, and then they come back out again. So that is another neat little thing just to look at, that we all have the same parts. It's just how developed they are, and what is the difference between the mammal and the amphibian and the bird and so on. Well, here, any creature that's alert needs the system to tell us, wake up. So we call this the reticular formation, and it's part of what we call a reticular activating system, or the RAS. So motor part of it, make sure that our muscles and tone are alert when we're alert. So if we're awake, we have light tone sent to our postural muscles to keep us upright. A sensory component is what we call the reticular activating system. So you see that rising up here and giving information to all the brain to say, let's bring about alertness. And this will bring us from 0 to full if we hear a creepy sound in the night, for example. So our auditory nerve signal, while we're asleep, we're unconscious, but our brain is very conscious, and it hears something that could be harmful to us, we wake fully ready to go. Or if the alarm clock goes off, we wake kind of ready to go and hit the snooze button and go back. But either way, that brings us awareness. Without alertness, we can't have awareness. So once we're alert, then we help bring about the awareness of sensation, and that's how we get to the next level of consciousness. So the way we understand consciousness, which is still a big mystery, and we got a lot of stuff we know what's going on, but there's a lot of mystery out there yet. Things for you guys to work on in your career if you wish. So we begin with, can we bring a state of alertness to us? Then can we bring in awareness? And then can we turn that into learning and be able to grow and change based on things that we're learning? But we need those early stages to get to the next stages. Nothing I would test you on here, but just so that you know that there are different sounds we can pull up from the brain. And we use an electroencephalogram, which we call it EEG, to record this. You can do it without the cap. We can find specific parts of the skull and lay in the electrodes by sticking them and then having a little gel weave between them. But the caps are so much nicer because their electrodes are set where we're looking, and we just set them on. And again, you have the jelly in between. We usually use a little injecting solution through that, and that will give it a medium so we can hear what's going on in there. Brain waves, they're Greek letters. The ones that are most common that we'll see when we're awake and doing stuff are called beta, and they're all measured by hertz. Nothing for you to memorize here, which, in case you're ever part of one. If you're awake but resting, the waves are a little farther apart, and those are called alpha waves. When you fall asleep, we move to an area called theta, where we drop to low hertz. And then the deep sleep goes even lower than that, and those are called delta. And you'll hear these talked about in looking for consciousness or looking for epilepsy, trying to see if there's a seizure activity, because that will show up very clearly as a disturbance in this. And then also the state of the body. We can use it to diagnose, we can use it to seek issues with seizure activity, and if the EEG is flat, a flat line, that's what we would call brain death. So this last part is, again, to this point, this was different when I learned it 30-some years ago, and it'll be probably different when you're later in your career. But this is how we understand it at this time. How do we process information to make what we call memory? The model of this has shifted a lot toward a more computer model, because we understand that more now. When I learned it, we didn't have much in the way of home computers. I don't know if we had any, so I learned it a little differently, but let's go through how we know it now. And you know these as things on your, even if you're not a computer person, you know this is a point where on your phone or on your computer desktop, it'll say, no more memory, you're out of memory. And the ones we talk about on those are random access, RAM, and ROM, or random operating. So similarly here, we have a short term and a long term, where we have things that we're working on at the moment that have to be spinning, and we can only juggle so much, and then we have things we're going to put away. What's different about us in that, or which closer to the internet, where there doesn't seem to be a limit on what we can hold long term. We seem to have an unlimited amount of memory in there, but this is a little bit trickier because we have to juggle what we're doing. And this, I always think of, oh gosh, how long has it been since you heard a certain song? Maybe you only heard it a handful of times, but it pops on the radio or in your shuffle, and you're like, wait a minute, I know this thing inside out. I know what's coming next. I know all the sounds that are coming. I can sing along. That's pretty powerful. That's in there still, and why, I don't know. But music has a real neat way of getting into your memory. So we define it as, how do we store and retrieve information? We call short-term things that happens over the seconds, and then we'll call it for up to a few hours. And research has shown us that the human brain can only hold on to about 7 good pieces of information at a time, juggling in that little circle. More than that, we start losing it. So those pieces of information, we choose what's salient to us, what's the most important thing I have to remember in this scenario, and that's, again, something you can train on. You can try to build that higher, but that's where we're operating right now as we understand it. If we choose to encode that through repetition, we will move it into here. That is encoded over time into long-term memory. That happens in our little hippocampus down here and says, this is worth holding on to. So we're gonna repeat it, and then eventually turn it to long term. It takes quite a while. And we don't seem to have a limit on how long you can hold on to that information. But we also suspect that if you don't retrieve it now again, it'll go away. So I think of the calculus I learned in high school, I haven't touched that since, and I couldn't sit in a calculus class and follow along anymore. But at the time, it was zipping around in there, it's just, didn't choose that path. And then just two types of amnesia we can talk about. Amnesia means problems with remembering. So anterograde, we can't add new information into our memory, but the old stuff's there. So we'll see this often in dementia, where we lose current events, but in their mind, they are somewhere where maybe it was happier. They're waiting for the kids to get off the bus. They got their purse and they're waiting at the door because they got to go to work, because the husband's coming home, and all those people are long gone. But if you've worked with that, you know how real it is to them. And then retrograde, you can't pull back the old things. And again, and I love that we say data because that's our modern idea of what's going on. But know that all of this comes through a stimulus. Something in our sensory information sets us up as a sensory memory, which is a fraction of a second. But if we attend to it, because my brain is picking up everything that's going on around me, but I'm not really aware of it except what I'm trying to be teaching. So my memory is focused on what I'm doing, but I'm somewhere in my brain, I'm aware of everything's going on in the room. I'm not attending to it. So as we attend to it, which this right here is where attention deficit issues break down, because the sensory information is like, ooh, wait a minute, and then we lose our thread. The long-term memory will only form if we've repeated a short-term memory, we encode it, and then if we can retrieve it, we go back to this. But if we forget, we've lost it.
Is that why sometimes you wake up and you know the dream you had, but then
that always puzzles me. Dreaming, again, another thing, we don't really know what's going on up there. Why we dream, people will tell you that you're in another universe, you're living a past life, whatever. I think we're just processing, this is my opinion, we're just processing stuff, because the dreams that I tend to recall that happen are either things that I'm worried about or they're on my mind, right? So I'm just going through there and I'm kind of working it out in my brain. I think it has to do with where you wake up during the dream cycle. So I think if you wake up in the middle of it, it's there, but then it goes like wisps. You're like, oh, hold on, you try to write it down to remember. I don't know why we care, but sometimes it feels like it's important. Like somebody's trying to tell me something. But other times I wake up and have no memory of dreams at all. So I think it's where you are in the REM cycle, which takes you back to this. So if you're in this is what we look for in the REM sleep, which is rapid eye movement. So if your eyes are doing this, now your body would be doing it too, but you actually send a signal down here to paralyze yourself. So we shut down the body, and people who sleepwalk or somnambulism, that doesn't work. So they just get up and start doing stuff. I don't know if you ever had that happen to you and somebody you're in the room with, but it's kind of weird. It's like, hey, what are you doing over there? And they're just going about doing stuff. But that's when this system doesn't work. So to answer that, if I can, I think that it's all in there. Things are happening, but there's no outside stimulus. So your brain is creating it off of something probably that you've seen and done already. It's stored and it's processing it, maybe to get it to here. But then when you alert during it, it's like it's caught off guard. It's like, oh, well, wait, let's hide it all. I always feel like that, it's all going away quick. But it's because it's not real, maybe. But we do know from brain scans that if you rehearse something mentally, your brain operates the same as if you're actually doing it. So athletes and musicians, people who practice a skill, will have that same training by repeating it 1,000 times. I can't remember the golfer, I should know these things, but somebody asked him about making a good shot. He goes, well, I've already shot it 1,000 times in the head. I just had to go out there and do it. That's what we know about that. So this stuff, I can get way deep in the weeds on this because this is my favorite topic, just trying to figure out what's going on up there. And in all my career, I've been working with people where it's not working. That's where you really see the effect. When you have someone in your family describes them as they were not like this yesterday, and then it's just what happened in there, and then how do they get back if they do. And that road back is where I've spent my career trying to help people find their way back to who they are, remembering families that they don't remember. We go through the memory books, the pictures, and it's just heartbreaking to a family if they lose that piece. So when a family member comes in waiting for their loved one to wake up, that's another piece of information I try to impart, that they may not know who you are. Don't take it personally. Don't be hurt by that. What happens, they're really in some serious recovery phase, and you might have to start your relationship all over again, which might be a neat thing. It's awkward when, and it's always happened to guys in my experience, but when the wife comes in to visit, but then out in the hall it's the girlfriend who's like, and the wife's like, oh, there you are. And, oh, but the guy, then God forbid the guy asked for her before she asked for her, right? Guys just do stupid things. Somehow we think we can always get away with everything. I don't know. Anyway, it has nothing to do with anything. I'm just, emotional state, right? So, these are things you will encounter in your role of caring for people. You'll get into their lives in ways you never thought possible. You'll be, just doing your job, and then some drama will happen, and the next thing you know, you're swept into your psychology training and say, okay, let's, or you go straight to criminal justice training and call in the troops to break up the fight. Particularly in brain injury, I found, because it's so traumatic, it's so sudden, and it usually happens with an incident like a car accident or a bar fight or a suicide attempt, that there's so much on the line, and everybody's waiting for this, whether it's the police waiting for the person to wake up because he's in charge of the crime, or the family member waiting for him to come back because they don't know what happened to him. It's so emotional if you get in that work. There's the Northeast Center down in Lake Katrine. I haven't been there yet, but I sent a lot of students there. So my work mostly with the Sunnyview Hospital with the coma recovery unit. We'd have like 3 months to work with people, which is rare in these days. But when people are coming out of a coma, we don't want to rush them. So that was a big part of my early career, and that just stuck with me. And then I think the hardest thing I ever did was working with babies and brain injury in St. Margaret's. If you've heard of that, it's a long-term care for children, but more young adults there as well, because they don't move them out if they can't, if they don't have a home. But many of them are on ventilators, many of them are victims of abuse, or just terrible, terrible stories. But that is really hard for me to recall those times, because it's so just watch what you feed your little babies. I have several hot dogs and rape stories, just get caught in the throat. A lot of overdose, a lot of suicide attempts. And I think those are the hardest too, that when someone tries to commit suicide and fails, but now they're permanently damaged from it, that there's a lot of mixed emotions with the surviving family members. They're like, they're angry, but they're happy that they're there, but the person didn't want to be there anymore. So it's this real mix of okay. So these are the thoughts. Emotional states, since I brought it up, I tend to teach, I like to teach, and I like to learn in a scenario where I feel encouraged and we're collaborative and we're not scaring you. Some of your learning experiences will be frightening going forward, especially if you're in the nursing program where you're under pressure, you're on a unit, and you have everybody looking at you when you're doing something with a real patient, and they're like, you'll be emotionally charged, but know that we're there to teach you, and we're not trying to, if you watch enough medical shows, we do humiliate each other, but we don't mean that. We're just trying to, make you the best person you can be. The emotional state of you learning will hold on to a memory harder. So if you had something happen to you, like, a first date or a last date or a big flight, they'll stay much more than the mediocre days that we just hung out and watched TV on the couch. Rehearsing it, which we had talked about in the brain activity, practicing. Do that before your next, or your final. I think the only big test we have left, we're going to do one for the brain, I'm sure, and then you'll have a final exam in lab. But rehearse it. See yourself walk into that room, get on the little blue shields and say, I know what this is. I know that, I'm writing it down. I'm writing all the letters, I'm spelling it out. Corpus callosum, you got it, and then just rehearse it. And if you can walk through the actual room and do it, that's even better. If you go back to the place where you did it, the context, it'll stick better too. So if you can get into the lab to practice, do it. And if you can't, get the models in the other room and just set up your own test. And that is so much easier than just trying to think about it. And then what we mean by long-term memory. Again, best of understanding. So we're limited to how many neurons we have. But if we're using this neural network over and over, and let's do a couple different ones, where let's say I'm going to talk to both these guys, and I want to talk to all three of them, I'm going to build stronger synapses by sending more neurotransmitters, building more receptors, and then I'm going to branch further to add more. I'm going to talk to you again. I'm going to tell you a second time. I'm going to tell you a fourth time. Now the network is stronger. So we refer to it as I like to think of it as planting. So when you're laying down a good trough in the ground to plant your seeds, you're setting up a really strong place for those seeds to grow. when you get distractions or damage or things going wrong, that's like weeds getting in and blocking their message. So the plasticity of the brain, the ability of the brain to learn and grow, and we do this all the time. We used to think by age 7 or so, your brain stopped learning. That was a big myth. But we would also think that after a stroke, you get about 3 months to recover and then you're out of luck. We also know that's not true. But insurance companies kind of limit us to that. That's another story. But your ability to heal and grow is never limited. It's just when you give up on yourself or when your other issues get in the way and life takes over and the brain is kind of just trying to, I think you said it, low-key lazy, just kind of do its thing. It doesn't want to do this much work. It's a lot of work to build new synapses and new neuronal connections and set all this up. So this remodeling of synapses and the new branches of axons and dendrites is how we build memory and how we build rehearsal and practice. So people who are training and learning, and you guys are all doing this every day, remodeling your brain as you go. Think of that, give yourself credit for how much you're doing up there. 2 different types of memory we talk about, and this is why we test 2 different ways in this course, because it prepares you for what's coming. We have to be able to recall things directly and infer things and figure things out. You're not going to get a lot of this in your nursing boards. You're going to get, tell me, here's a scenario, you figure it out. Where declarative fact memory is this basic facts, which we're throwing in the lab. Well, all you have to do in the lab is, there's a couple of questions we'll ask you, but mostly it's like, what is that thing? And you have to know it. And that's your explicit information. Name, face, word, date, give me that. It's conscious thought and language activity, and it's best, again, where you go back to where you learned it. So if I see you guys outside this classroom, I won't know who you are. I try. I know you from somewhere. But I'm always, encountering new people, and if I'm out in the public, it always takes me a second to say, did I meet you at school? And that's fairly common, I hope. Either that or I'm just losing my memory. The other type is called non-declarative, where it's more of a motor activity. This is practice. This does not really matter where you learned it. This is something that you've done through rehearsal. So you've trained this is what we call, people mistakenly call it, blame them for it, they call it muscle memory. So say, oh, I've got muscle memory of that. Well, the muscles don't really remember. But what does remember is the brain, particularly that pre-motor cortex. So once you set a pattern in there, and I always talked about it, it's like a floppy disk that you put in, and we don't have those anymore. Now it's an app you run, or however you want to think of it. It just runs by itself. So you don't have to motor plan it anymore. You say, I've done this enough times, you know how to do this. Plug it in, and your brain just does it for you. So playing a piano, it's a skill. Riding a bike is a motor memory, what we call muscle memory. And then something like this is emotional memory. These are harder to break, as you can imagine, because they're tied to some survival instinct, often when you're a child. But this is what long-term therapy is for. You work your way through it. And there's different approaches. Do I expose you to it, or do I rationally talk you through it? It's very hard to rationally talk through an emotion. But it can be done. It's just, this is why there's therapists and drugs and things that we work on. But that's what we mean by different types of memory. Language, as we hinted at, is very, very complex. And it's fairly unique. All creatures communicate in their own way. But for the humans, we have a very specific set of things that we do and areas that we've identified on usually the left hemisphere. And the big players are the prefrontal, which is our maturing brain. This is not really mature until late in our 20s. I often joke that it matures far quicker on women than men, but I believe there's some truth to that. We just don't have a reason to get mature very early, where women tend to be more on the ball. At least, give the guy time to figure it out someday, maybe. Motor speech is here. Anything prior to here has to be motor, so motor speech is Broca's. Wernicke area in the back is where you're hearing. So Wernicke interprets it, and written language. So you have the ability to, because all we're doing in language is saying this weird shape is going to match to some sound that I've heard. And we put them together through practice and watching somebody's lips. That's where so many kids now that I'm working with are struggling in this area because they have masks on themselves and their teachers when they were learning to speak. So during the pandemic, we didn't have the full loop of hear, see, repeat, read, and we lost that huge. It's been really devastating for that generation. Motor speech area has to imagine, just like I was saying, I see you do something, I want to try doing it. I see your mouth move a certain way, and you watch babies, and you're like, yes, and you give them that emotional rush of yay, wow, mom's really excited that I said mom, accidentally, like woohoo! So that is how we learn. And it's so devastating to a parent when a child, say on the spectrum, they shut that off, they're not interested, they don't make eye contact, they have no interest in doing that, and it's so hard for the parent to say, but that's the whole reason I had you, so you could be my little buddy. Just have to learn how to love them in a different way. You're not expecting those things. And unless you put pressure on a child to do something that they're not, capable of, that's easier on you both. Another story. But that's your area here. And then the primary motor cortex lines it up and says, I've witnessed this, I've practiced it in my head, I've done all the things, and now you can repeat it. So why do we know all this? Because people had these things happen to them, and we're like, oops, I guess that area is very important because now they can't talk anymore. Or there they wouldn't talk to, they can understand. Both of those are called aphasias. Just to show it more time, this is a receptive aphasia. They don't understand what you're saying to them, so if you're talking their language, they'll look at you like, sometimes you can write it, that'll help. Expressive, they can't say what they want, things will come out that aren't what they want to say. They'll be surprised, they'll have foreign language, they'll have swear words, they'll have nothing. They'll have gibberish. We also call this a word salad, when you come out and you just make nonsense. And then if they combine, we call that global aphasia, we lose both. Again, sometimes writing will get you in, but it's usually best with a picture, like yes, no, point. Give me a physical output instead of trying to make the mouth work. And that's where speech therapy excels looking at that. And that's our unit. Last one, we have one left, is senses, and we'll do that Wednesday, and I'll give you back your test and we'll go over that too.